Welcome to Brain Vision.
Hello everyone, so what we have is a steam turbine that has an incoming pressure of 1.6 megapascals and an incoming temperature of 350 degrees C. And at the outlet we have saturated vapor at 30 degrees Celsius. We know the m dot going through the turbine is 22 kilograms a second, and the power output is 12,350 kilowatts. What we're asked to solve for is the rate of heat transfer that is lost through the casing of this turbine. Let's just go ahead and say our assumptions. So we're going to assume that this process is steady state, and we're also going to assume that kinetic energy and potential energy changes are negligible. So what we can do is go ahead and look at our steam tables, and we'll see that for state 1, which has a pressure equal to 1.6 megapascals and a temperature equal to 350 degrees C, that our incoming enthalpy will be equal to 3,146 kilojoules per kilogram. And for our exit state, we know that our temperature is equal to 30 degrees C, and we do have a saturated vapor, so that means our quality is going to be 1. Therefore, this gives us an exit enthalpy equal to 2,555.6 kilojoules per kilogram. Now what we can do is define our system. We're going to define the turbine as our system, and that's also the CV. So we can actually go ahead and write our energy relation. So we can say that the rate of energy coming in minus the rate of energy exiting is equal to the change in rate of energy of the system. However, we know that this process is steady state, so the change in energy of the system rate is going to be 0. Therefore, energy rate coming in is equal to the energy rate exiting. Now we can actually go ahead and define our energy coming in and energy exiting. So we have steam coming in at an enthalpy, so that's going to be m dot h1 is going to be equal to the exiting enthalpy plus the work that is extracted plus the rate of heat transfer. So what we can do is actually just go ahead and solve for the rate of heat transfer and say that q dot is equal to m dot h1 minus h2 minus w out. Now for plugging in for all of these variables, we'll see that we get a q dot equal to 640 kilowatts, and that is the heat transfer that is lost through the turbine casing.